Okay. Awesome. Yeah. As Ron just mentioned, I'm going to be talking about uh, how to understand the local learning coefficient as a fractal dimension. This is sort of a small result that I found helpful, kind of pedagogically, uh, but haven't hasn't been sort of published anywhere yet. So I'm hoping this could be useful sort of as a resource. There's also some notes that I put on my website, some brief notes that I link at the end. Um, yeah, so as some context, so maybe obvious, but there's sort of two separate perspectives we're bridging here. One is from singular learning theory. Uh, Singular learning theory talks about how singularities in machine learning models show up in learning dynamics and reflect the sort of learned algorithms and things like that models have. Um, and in particular, the local learning coefficient is what we use to measure the effective dimensionality of a machine learning model, um, accounting for its singularities. Now, in parallel, a completely separate field, fractal analysis studies fractal characteristics of data. Um, and its primary tool is fractal dimensions, which characterize also the effective dimensionality of data, but in a completely separate context. Um, and um, yeah, so these are two a priori kind of very separate fields, but with both having this sort of notion of effective dimensionality. Um, and I'll sort of explain uh, precisely where that kind of coincides. So actually, most of this talk is just going to be recapping basic singular learning theory and basic fractal analysis. And then once I've done that, it's pretty straightforward to show how the local learning coefficient is equal to this particular type of fractal dimension, the local dimension under some conditions. Um, okay, so I'm gonna remember some basic singular learning theory, um, and just enough to sort of uh, connect with what we're doing here. So the first thing to review is what I mean when I say that a model is singular. So we're talking about singular learning theory. What is singular? Um, and I'm actually going to highlight here a particular distinction, which there's actually two choices you could make here. Um, One of these is this sort of notion of model singularity that a parameter that is sort of a tangent direction in parameter space is singular if moving in that direction doesn't, to first order, change your predictions on any input data. That's sort of model singularity. And then there's a loss singularity, which is where if you have some tangent direction where moving in that direction up to first order doesn't change the loss. And these are very closely related, as I'll discuss in a second. And uh, Sort of law model singularities basically always imply loss singularities, but not vice versa. But oftentimes, the traditional setup in singular learning theory is to sort of uh, work with these loss singularities, but often establish conditions such that you're effectively studying model singularities. This is maybe like a distinction that's kind of implicit in a lot of the theory, but I'm going to make it explicit here um, for reasons that I'll explain shortly. Um, I'll sort of expand on this distinction. Yeah, model singularities, the predictions don't change across all of the data. So you see this little diagram, like the probability of x1, x2, x3, etc. Um, all stay the same. Uh, and this what's interesting about these, it only depends on the parameter function map. Uh, so and sort of where in the parameter function map you're looking, what parameter. Um, Whereas loss singularities sort of also depend on this true data generating distribution. Um, Assuming, as singular learning theory does, that you're using some kind of like Kale divergence or other statistical distance for the loss. Um, so you need some true data generating distribution. And so the loss singularities are quantified by this ordinary local learning coefficient, but model singularities are quantified by this behavioral local learning coefficient. And this is important because the behavioral local learning coefficient is going to be what we're going to connect with fractal dimensions. So I'll sort of define the um, behavioral local learning coefficient, which is almost identical to the definition of the ordinary learning coefficient. But I'll just run through it. Actually, I'll do that. Sort of, if you haven't seen a singular model before, this is a pretty simple canonical model to have in your head. Um, so an example of a regular model is a Gaussian we have on the left. Example of a singular model is this cubically parameterized Gaussian like we have on the right. These are equally as expressive um, in that I can any Gaussian on the real line, I can find some W for both of these models that will fit it, or I guess with any Gaussian with this is unit variance. Um, but uh, at um, at W equals zero, the sort of sensitivity to W equals zero is very different. So the Gaussian model is totally sensitive to perturbations at W equals zero, but the singular model isn't, and that will change this sort of uh, this sort of local learning coefficient between between these two models. Um, yeah. So what is this behavioral local learning coefficient? So you have to define this sort of volume of all parameters in parameter space within epsilon KL divergence of let me say the behavioral local learning coefficient, right, is about it's local, so it's about some parameter W star. Okay, so W star is the parameter that we're measuring the local learning coefficient, the sort of behavioral um, local learning coefficient about. So what we do is we look at all parameters in parameter space within epsilon KL divergence of the model uh, at this parameter. So this is sort of KL. The KL divergence is again like a statistical distance. So we're sort of looking at how many parameters in parameter space are within this sort of distance in function space, sort of this particular parameter. What is the volume as a function of this sort of tolerance epsilon? Uh, and then the behavioral LLC is this sort of unique number lambda of W star, where if I just take epsilon to zero, it turns out that this volume goes basically proportional to epsilon to the lambda. There are some low order terms. You'll see this sort of logarithmic term that I've grayed out. These are sort of less important for the intuition and I'll be doing various things to basically ignore that term. But yeah, just think of it as epsilon to the lambda. So here's sort of two examples of what I mean. So on the top, I have a regular. Um, oh, actually, that this proportionality constants are wrong. That should be, I think, that should be epsilon. I think to the negative one on top, or yeah, and yeah, that should yeah. Okay, those are wrong. Epsilon to the one, uh, and this should be epsilon to the one third, I believe. Yeah. Um, so these are two different 2D models. The one on the top is this regular model, which is just a quadratic um, potential. Um, the one on the bottom is sort of a sort of normal crossing model, um, and uh, the singular geometry sort of means that the surface area here grows much faster. So if you look at, in this case, V of epsilon is this sort of surface area in parameter space, and you notice like on the bottom, it's sort of just that area just sort of appears immediately, very quickly. Whereas on the top, it takes a little bit more time as epsilon increases for that area to kind of grow, and the fact that it grows faster is shows up in this LLC being smaller. Uh, if that seems confusing, remember that we're looking asymptotically as epsilon goes to zero. So when we're looking close to zero, a smaller LLC means grows faster. Yeah, okay. So the important thing here is to know is that for regular models, this is just going to be half the parameter count. So kind of boring. But if in singular models, like neural networks and things like that, um, this can be, it will be less than uh, less than half the parameter count. Um, So, and this can change depending on where you are in parameter space. Um, the this isn't a uniform measure across parameter space, but actually can change. Um, and then I'm just going to sort of briefly like explain a little bit why I've like kind of introduced some of this new terminology here. This is some terminology we use kind of internally, but I can sort of explain why I've bothered here. And because it turns out that actually this behavioral LLC is just actually the same as the ordinary LLC in the case where the true distribution is the one you get at W star, the point you're looking at. So why bother with the whole behavioral LLC terminology? Why not just say the LLC where the true distribution is W star? And the point is actually to highlight that this is not some special case of the LLC or something like this. Um, this is actually, in some sense, equally fundamental. We're sort of looking at an intrinsic property of the parameter function map. Um, and how the sort of measure concentrates under the parameter function map. And uh, this is this is sort of an intrinsic property I want to highlight. Um, this will be kind of clarified by this fractal dimension connection. Okay, so now I move on to the fractal analysis part. So I'll just sort of briefly go over
Can
what
I
a
ask
fract.
a quick
Yeah,
question?
Yeah, go for it.
So I noticed that in the behavioral LLC, you only have an X and no Y. Um, is that so? Should we think of this as a generative model then, or is this
Uh, no, so that's it's sort of agnostic. So I mean, you could think of uh, so this actually works for both regression models or generative models. For a regression model, what this X um, would include both the inputs and the labels. Um, and you would have to have some. So actually, I mentioned this sort of briefly, but yeah. So this model singularities depend on the parameter function map, which for like a generative model would just be the architecture. If you have a regression model, you also need actually there's implicitly the input data distribution. So there's another object that needs to be defined, which is typically and for a regression model, you're only parameterizing the conditional uh, of the labels on the inputs, and you'll need to um, say what the distribution on the inputs is. Um, but yeah, this is sort of also within the framework.
okay? Thanks.
Yeah. Um, yeah. Any other questions before I move on to the fractal analysis part? I'll also take questions at the end. Awesome. Okay. Yeah. So what do I say? What do I mean when I say fractal? Um, so we're sort of typically used to these kind of smooth objects with integer dimension, but in nature and a lot of complex systems, we find things that break this. So actually, in some way, this was the problems were first noticed maybe in very niche mathematical. It sort of seemed like mathematical contrivances, but actually we've sort of later found that these are in fact very real world uh, objects. Um, so there are so mathematicians often sort of can't agree on precisely what a fractal is, but they agree there's sort of these two um, aspects, which is one is sort of self-similarity. So here's this sort of Cook snowflake, so a particular kind of fractal. Um, and another, which is quite important, uh, is fractional dimension. So they sort of seem to fill space more than a line, but less than a plane, for example. In fact, this often can be like in many mathematical considerations, like this is actually the defining quality of a fractal is non-integer fractal dimension, and this is actually going to be the important quality for us too. Um, Okay, so I'll first explain the more typical kind of notion of global fractal dimension that you might be more sort of familiar with like a box counting dimension. So I sort of you saw this coastline of Britain kind of example. So how would I measure the length of the coastline of Britain? Well, my answer is going to depend on the length of my ruler. Um, so actually what you want to do is measure how the length of the coastline changes with the scale of my ruler. That kind of gives you a quantification of dimension that's not dependent on um, the uh, a particular choice of length scale. Um, so one of the simplest fractal dimensions you can define is this box counting dimension. So you just cover the space in boxes of a particular size, and then you see what happens as I decrease that size. What's the sort of power law you get? So I have the three examples there on the right of just a line, a plane, and a cube, um, where you see, uh, you know, with a line, it's just 1 over epsilon proportional to 1 over epsilon number of boxes. For plane, it's 1 over epsilon squared. For cube, 1 over epsilon cubed. So for normal spaces, like a line, plane, and cube, this recovers this sort of ordinary notion of dimension. But for things like the, coastline of Britain or something, it can recover a non-integer dimension. So then you can move from here to more complicated notions like the Hausdorff dimension is one of the most popular fractal dimensions. Um, Not going to go further in this direction. It's just sort of mentioning this as the most common kind of fractal dimension you'll typically encounter when you hear about a fractal dimension. Actually, the notion we need is more local. Uh, so, uh, like from again using this coastline example, you might have some very like rugged cliffs that have a higher dimension locally than some smooth beach, and we want to be able to quantify that dimension locally. So this local dimension is defined for a measure mu. And if you have a distance to sort of define these balls, b of epsilon, and a point x that you're defining it about. So you can see I have this example of the Cook snowflake, and you can see we're sort of uh, looking at how much of this little snowflake is contained inside the circle as I shrink epsilon. Uh, and this will give you that same sort of power law kind of behavior in epsilon. And alpha of x is this sort of local dimension at x. So it can change, uh, which is useful for us because we want our dimension to be able to change depending on your parameter. That's pretty important. Um, and yeah, I'll just sort of briefly mention uh, where besides singular learning theory, this stuff shows up in a lot of places. So like you can, for instance, in material science, look at fracture surfaces, count up the boxes that you literally see in your image, like take a physical image, count boxes of different sort of pixel sizes, and see how that changes and literally quantify the sort of complexity of the kinds of cracks that you get in your materials. You can sort of use this to analyze the sort of inside tissue of your bone and how healthy it is. Um, Based on its the sort of medical imaging that you can get. The local dimension you can apply to a lot of things like transient detection and like finance and any kind of like time series data, texture analysis, also in medical imaging. Um, a big application of this local dimension is to multifractal analysis, applied to sort of dynamical systems and chaos theory. Um, which I'm not going to get into, but that's actually a really interesting connection and direction for future work, sort of multifractal analysis angle. Um, okay, so now the payoff, how is the LLC a fractal dimension? So at this point, hopefully you've already seen that we've had some pretty suspiciously similar equations, right? This volume scaling formula we use to define the learning coefficient, if you sort of ignore again that logarithmic term, and then the volume scaling formula from the local dimension. Uh, and yeah, can we formalize this? Okay. So just remember that this local dimension that I presented right here, uh, there are three ingredients, which is a measure. So you're going to need to measure some measure of points in your space. you're going to need a point X in your space, and you're going to need a metric to define these balls be epsilon. Okay, so we have these things. So for measure, we have the uniform measure on parameter space. Or if you want to be Bayesian about it, you can use sort of your prior distribution, so long as it doesn't, so long as it's supported everywhere um, on on your parameter space, which we're sort of implicitly assuming to be compact. Um, the you need we need this point X. So we're going to use a parameter W star, and we need a metric. So we'll use the Kale divergence question mark, except that's not actually a metric. So to just be formally correct, we're going to use the Jensen-Shannon metric, which is very closely related to the Kale divergence, but it's sort of symmetrized and square root of the Kale divergence, just to make things work uh, technically, so that we can use the existing definition of the local dimension as it is without patching it. Um, and then here's the result. Um, so if lambda is the behavioral LLC, um, then uh, it just turns out that the local dimension of a point under the uniform uh, measure and the Jensen-Shannon metric, that's just equal to twice the local learning coefficient. In the case where this multiplicity term is one, this multiplicity is one, which is kind of if you would call this sort of equation here, this M of W star, if that's one, then that lower order term is dropping out. So we're basically saying ignoring the lower order term, you get this equality that this local dimension is twice this behavioral LLC. Um, okay, so let me unpack this a little bit. Why should care? What is this sort of? Can you sort of interpret what this means, right? So singular learning theory. Oh,
Sorry, sir, can I ask a quick question? So why do
yeah.
you actually need the assumption m equals 1? I mean, the lower order term is actually lower order, right? And the dimension is defined as some kind of limit. So shouldn't it drop out automatically or something?
Yeah, the problem is that you have to define the limit differently than how so so the limit is the way that you would typically define this limit that's not in the presence of this lower order term is like the limit of the logarithm of this measure divided by the logarithm of epsilon. But the problem is that actually this will sort of if you have this log term, this will end up causing um, causing problems. Yeah, I don't want to make like a wrong statement here, but uh, this you often have to. So the way Watanabe does it is you take this limit uh, log of you take log of um, v epsilon uh, v you take log of v of a times epsilon divided by I think a v of epsilon uh, over log of a, and then a is just any constant which is not one, uh, and that fixes the limit, but uh, it changes it slightly from how like in some sense you have to deal with these uh,
I'm a
this
little confused. Like, I'm looking at this equation and I take the log of both sides, then I see that log v equals to log C plus lambda times log epsilon plus something times log epsilon. So when epsilon goes to zero, log epsilon goes to infinity. So log epsilon grows, if we denote now change variables instead of log epsilon, let's call it just t. So t goes to infinity, and I have term linear in t and the term which is log epsilon, which is logarithmic in t. So if I divide it by t, then this term should just vanish in the limit, right? Because it's just log t over t.
Guess it depends what you mean by the approx symbol there. I mean, if you mean leading terms of the asymptotic the same, then yeah, that's right. But I think
Okay.
that isn't
So,
how, I mean, Zach, I'm not sure exactly what you mean by approx there, but I think it,
Yeah, leading term in an asymptotic expansion, leading order term.
I mean, I feel like if it was an exact equality, then everything would be fine. So it seems like the problem is not with the am, but with the approx, which
Okay.
is
Yeah.
confusing.
Yeah, I see your logic, and yet uh, recall there being an issue here. So I like uh
I
I
mean, there
want
there might be
I want to
something
agree, but I
unique.
would need to like sit down and double check this. But what you're saying like tracks. Uh
I can imagine there's some nuance when you go from KL divergence to the JS metric that somehow gets this M involved, but I have no idea how would that happen.
yeah, I don't think it was an issue with the going from the Kale to the Jensen Shannon, but yeah, I'll have to look at this again. I mean, there's a reason why Watanabe takes the limit in a slightly weird way, and it's because of the multiplicity term. But yeah, maybe things get easier under the Jensen Shannon. Uh, yeah, I'll have to sort of look at that.
I think it's just a question of whether you want to study the asymptotic expansion of the logarithm or of this thing itself. I mean, they're not the same, right? So, like, I mean, obviously they're related, but uh, yeah, I mean, you don't need to perform this thing that Watanabe is doing if you only want to talk about the logarithm.
hmm Yeah, okay. Um, yeah, okay. I vaguely remember there being problems when I tried to eliminate this, but that all seems to make sense to me. So, yeah, it may be that you don't need this condition. Uh, yeah, in which case that would be nice, and I will just update my notes to fix that if that's true. Um, yeah, that would be good. Okay, so uh, either way, I think there's this similar kind of takeaway, which is uh, that okay, what we're actually doing here, when I sort of went through that correspondence is right, we are actually let me step back and say one of the more fundamental things we're studying in singular learning theory is the structure of this parameter to function map and the kind of really extreme non-injectivity or insensitivity of this map. Um, and what we're doing with this sort of definition, this sort of correspondence, is we are measuring density using the measure we sort of inherited from parameter space, but with a distance given by function space. This Jensen-Shannon metric is really about distances between different probability distributions. Uh, so what we're sort of implicitly doing is looking at we're looking at this measure of parameter space, and we're viewing it in function space using the distance in function space. So you can sort of see this as the measure on parameter space sort of defines an implicit prior on function space. So what functions are more preferred? Uh, just if I just sort of think that I'm looking at all parameters equally, well, actually that invites a very strong preference on functions if your parameter function map is very non-injective, because the parts which have more parameters, the functions which sort of have more uh, parameters dedicated to them will get higher sort of prior under this measure. The LLC is quantifying exactly how much this implicit prior is concentrating. So that's sort of what this local dimension result is telling you, is exactly how much of the uh, this measure in parameter space is sort of quantifying in function space. We're using that distance from function space. And okay, yeah, so that's sort of the important part. And then so some loose ends, which are actually uh, first one is we just talked about this, uh, and the second one. So I talked about the sort of connection to the behavioral learning coefficient. Um, is what about the ordinary learning coefficient? I think actually one an answer part of my answer to this sort of question would be like actually the uh, to resist the instinct to like sort of say that this isn't meaningful unless you can generalize it to uh, every type of learning local learning coefficient you get it in practice. Like you are actually learning something quite important about the structure of the model. But I still think that there's potentially important stuff you could say in the case where you're looking at this sort of ordinary learning coefficient rather than just this behavioral local learning coefficient. That would be a direction to sort of figure out. Um, yeah, so that's it. I have some notes at the QR code, which uh, just go through a little more formally, actually prove the statement I put uh, in that slide. Um, and yeah.
So I have kind of a conceptual question about this, which is like, is there something particular that you're hoping to gain from this kind of marriage of singular learning theory to fractal analysis? Is there like something where you say, oh, like fractal analysis knows how to do things such and such, and this is why I want to.
Yeah, there's routes you could go that I think have like particular applicability. Like I think there's like interesting things you could maybe do with like multifractal analysis. That's something sort of explored, um, which provides like particularly good tools for understanding how if I have a lot of different singularities with different local dimensions in a space, how that influences observables. Um, I think actually more sort of the reason I'm talking about this is more just pedagogical. Um, so I think like I found this is just a helpful kind of intuition for. I think fractal dimensions are as a standard kind of notion of measuring a dimension in sort of non-integer dimension in weird kind of spaces. And so actually, knowing that um, at least in a particular kind of local learning coefficient is just the standard, this existing notion of that's already out there, I think maybe makes this a bit less weird and kind of clarifies a little bit what we're trying to do here. I saw there
I,
was some message in the chat, but I can't.
That was just a link to your notes for people who
Oh,
didn't want
okay.
to type it out, I believe.
Okay.
um,
Yeah.
so I have a perhaps a somewhat silly question.
Hmm.
Um, so where is the fractal in the loss landscape? Is like if we see that the fractal dimension is something fractional, then we do we expect to see some sort of fractal like structure in the loss landscape as well, or
I think the short answer is no, in the sense of like if what you're expecting is like uh to see like some like Mandelbrot kind of set like in the lost landscape or something like that, uh the yeah, the answer is no, it doesn't. You're not necessarily going to see some kind of self-similar structure. What sort of has what is the sort of fractal in this case is this measure, this sort of uh, push forward measure of uh, parameter space under the parameter function map, and this does have a sort of self-similarity. So uh, like uh, this won't look like some kind of like really intricate Mandelbrot kind of structure. It'll instead look like something like, I think in that cubically parameterized case I gave, the push forward measure looks something like x to the negative two thirds or something like this. It'll be kind of something that sort of blows up. Um, at a particular point. So when viewed in function space, it'll look like something like that. And this does actually have a kind of self-similarity in that every time I zoom in near this blow up point, it's still blowing up. It's just not like this crazy intricate like Mandelbrot. It has these aspects of self-similarity and fractional dimension. It's just not like as like pretty or something as Mandelbrot said or something like that.
well, but I guess not space fillingness.
Yeah, not every. Well, it does have space fillingness. Mm, I guess it is sort of yeah, I see what you're saying. It's not going to be larger like so often, yeah, one way that you get these sort of fractals, like for instance, I have some function from the reals to the plane, which uh, is in some sense like very not differentiable, such that I can have this sort of space filling property. Um, since in machine learning, this map from parameter to function space is always um, uh, is always, if not analytic, like piecewise analytic, um, then you're just not going to get that egregious sort of map such that you get this sort of expansion in dimension rather than a contraction in dimension.
Gotcha. Okay. Yeah, thanks.
Yeah.
I'll just read out another question from the chat. Do you assume some sort of convergence or training? Like, does W star have to be the final learned parameters of the model?
Yeah, no, so that's actually a good point, which is because we sort of unlike the sort of ordinary local learning coefficient, which requires that you be at a local minimum of the loss. This works for any W star. Uh, so the way you could view it from that perspective is sort of um, this 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 behavioral local learning coefficient is sort of used as a surrogate loss, which is just given by the distance of the model sort of in function space to W star. And you can measure that, for instance, throughout training time at any point. Uh, even if it's not a local minimum of the loss, it will be a sort of local minimum of this KL divergence that you use in the behavioral LLC, sort of just by construction. So yeah, it works anywhere. There's none of these sort of local minimum problems that you might see with the ordinary LLC.